Thank you for the introduction, and I'd also like to thank the organizers for the invitation and for the opportunity to give a talk here. So, as I was telling you, I'm going to tell you about, I'm going to tell you about the initial value problem for the generalized surface quasi-geostrophic front equation, which reads phi t minus q of phi x equals 2 log of dx phi x with initial data phi of 0 equals phi 0 when alpha is equal to 1, and phi t minus q of phi x equals c of alpha times absolute value of zx to the power alpha minus 1 when alpha is not equal to 1. I'll tell you in a bit what the story about alpha is. So first, some notations. The nonlinearity q is defined as the integral of over r of 1 over absolute value of y to the power alpha minus 1, f of delta y f, absolute value of delta y g dy, where delta y f is the difference quotient of f, and absolute value of delta is the signed version, in the sense that we replace y, the denominator, by its absolute value. Capital F is a smooth function with a double zero at 0, given by 1 minus 1 over square root of 1 plus x squared, the power alpha, when alpha is non-zero, and 1 over 2 pi log of 1 plus x squared when alpha is 0. The constant c of alpha from earlier is given by minus 2 sine of pi times 2 minus alpha over 2 times gamma of 1 minus alpha, where gamma is Euler's function when alpha is not equal to 0, and minus 1/2 when alpha is 0. Let me tell you from the very beginning that the value of c of alpha is not going to be relevant for our analysis. Okay, so where do these equations come from? So these come from the generalized surface quasi-geostrophic equation, which consists of a transport equation where a scalar quantity, theta, you can think of it as a temperature, is affected by a velocity field u, which in turn is given by a Biot-Savart law. Namely, u is minus the Laplacian to the power alpha over 2 minus 1 applied to Nabla-Perp of theta, where Nabla-Perp is minus partial y partial x. Theta, as I was telling you, is a scalar function of one time variable and two real spatial variables. And minus the Laplacian to the power alpha over 2 minus 1 is just a fractional Laplacian. Let me also mention that in the SQG case, when alpha is equal to 1, the problem models quasi-geostrophic flows confined to a surface. And moreover, it also accounts to the formation of this continuous temperature fronts, which is a phenomenon known as frontogenesis. The case alpha equals 0 gives the 2D incompressible Euler equation, which we are all familiar with. And let me also highlight the fact that there are certain similarities and analogies between the 3D incompressible Euler equation and the SQG equation in 2D. So for example, level sets for the SQG equation correspond to vertex lines for the 3D incompressible Euler. And moreover, the question of singularity formation in finite time is still open for both problems. Okay, so front solutions for this equation refer to piecewise constant solutions with the following form. You have theta, piecewise constant function, equal to a value, theta plus, above a graph of equation y equals phi of tx, and theta minus underneath. And the equation that I showed you at the beginning describes the evolution of this contour, which is assumed to be a graph. Okay, the evolution, the equation that I showed you at the beginning, was first derived by Hunter and Xu in 2017 by a regularization procedure, and then together with Zhang in 2019 by a different method. Front solutions are also closely related to patch solutions, which are still piecewise constant solutions. The difference is that theta is going to be equal to theta plus in the interior of the open, simply connected bounded domain, omega of t, and to theta minus outside of this domain. Let me also tell you that the gSQG front equation is invariant under the following transformation. So In the case alpha equals 1, t goes to kappa t, x goes to kappa times x plus 2 log of absolute value of kappa t, which is akin to a Galilean transform, and phi goes to kappa phi. And in the case when alpha is not equal to 1, you get the pure scaling symmetry. The time goes to kappa to the power alpha times t, x goes to kappa x, and phi goes to kappa phi. In either of these two big cases, one can see that h dot 3 halves is the critical scaling Sobolev space. Okay, this is a summary of the results that are known up to this date regarding the well-posedness of these equations. So when alpha, for example, for fronts, when alpha is equal to 1, Hunter, Shu, and Zhang proved in 2018 that the problem is locally opposed in HS of R, where S is greater or equal than 5. Also under the assumption that the nonlinearity satisfies a certain series expansion. And they also extended these results to the range when alpha is between 0 and 1. When alpha is between 1 and 2, Cordoba, Gomez, Serrano, and Dănescu showed that the problem is globally well-posed for small and localized initial data in H20 alpha. And let me also tell you that Hunter, Shu, and Zhang also proved that the problem is globally well-posed for small, localized, and essentially smooth initial data. They worked in HS of R, where S is greater or equal than 1,200. Okay, now, what did we do? In a previous paper from 2022, we proved that the SQG front equation, and by this I'm referring to the case alpha equals 1, is locally well-posed in HS of R, where S is greater than 5 over 2, for large data as well. So we dropped the assumption on the convergence of the expansion. And that the problem is globally well-posed when the initial data is small and localized in HS of R, where S is greater than 4. In our current work, by making use of a null structure that the gSQG front equation exhibits for all alpha, we lowered both of these regularity thresholds when alpha is equal to 1 and then extended them to the full range, alpha between 0 and 2. So here is our main local well-posedness result. So when S0 is a parameter less than 3 halves and S is greater than 2, this is for alpha equals 1, and S greater or equal than alpha plus 3 over 2 when alpha is not equal to 1, gSQG front equation is locally well-posed in H dot S0 intersecting with H dot S in the Hadamard sense. To be more specific, for every positive radius R, there exists a time depending solely on the radius, such that for every initial data in the open ball of radius R, the Cauchy problem has a unique solution, phi in C of 0t with values in H dot S0 intersecting with H dot S. Moreover, the solution map taking phi 0 to phi is continuous. Let me also remark that by using these methods, we can also easily prove that the same result is true in the case when alpha is equal to 0, for what we would call Euler fronts. However, for the purpose of the next result, we'll only be concerned with the non-zero case. So let me also highlight the fact that when alpha is not equal to 1, we were also able to achieve the endpoint result, namely S equals alpha plus 3 over 2. Okay. For our global well-posedness result, by using the wave packet testing of Ifrim-Tataru, we proved the following. If phi 0 is some initial data with the property that it's H dot S intersected with H dot S0 norm plus the L2 norm of X partial X of phi 0 is small enough, where this time the constraints are S greater than alpha plus 2 and S0 less than 1, the solution phi, whose existence is guaranteed by the local well-posedness result, is actually global. And moreover, it satisfies the following pointwise bound, dx to the power 1 minus delta phi plus dx to the power alpha over 2 plus 1 plus delta. Phi and infinity is controlled by the Japanese bracket of t to the power minus 1/2 times epsilon. So quick question, how much time do I have left? 5 minutes? Yeah, maybe I should explain why our local well-posedness result, at least when it comes to using the energy method, is optimal. So yeah, let me clear the board a little. Perhaps I'll use this one. Okay, let's look at the level of the nonlinearity. So let me remind you of the expression of the nonlinearity. So our equation was this. Phi t minus q of phi phi x equals c of alpha or 2 log dx partial x phi. Doesn't really matter. What I want to tell you is that, so this equation has a linearized counterpart, which reads vt minus partial x of q phi v equals c of alpha dx to the power alpha minus 1 partial x v, or 2 log of dx partial x v. We're not going to be concerned with the dispersive term here. Our claim is that all the action will happen here in the nonlinearity. And let's expand its expression. This is partial x of the integral of f of delta y phi, absolute value of delta yv dx. And let's say that we are trying to prove energy estimates for this linearized equation at the level of L2. So v is the unknown, and we want to put v in L2. Let's assume that we can, so what do we have here? F is quadratic. This is essentially like partial y of phi squared. So basically 2 factors of phi. Let's assume that for the time being that we could move derivatives around as we wanted. Move them away from v and distribute them onto phi's. How many do we have here? There's 1 from here, minus 1 from the integral, when I forgot about the 1 over absolute value of alpha minus 1. So alpha minus 1 derivatives, plus 2 derivatives from each different quotient or on phi, plus another one from the difference, sign difference quotient of v. And this gives what? Gives alpha plus 2 derivatives. Now, we want to put 2 factors of phi in some pointwise based Sobolev spaces or BMO spaces, and v in L2. We have to distribute alpha plus 2 derivatives onto 2 factors, just so that we have as few derivatives as possible, because we want, in our Sobolev embedding threshold, to have as few derivatives as possible, right, if you want to achieve a low regularity result. The only solution is to distribute them evenly. So basically 1 plus alpha over 2 derivatives on each of these 2 factors. And at the level, so this is at the level of BMO or L infinity. By Sobolev embedding, if we go to the level of L2 based Sobolev spaces, this gives the alpha plus 3 over 2 that I was telling you about. Okay, so this is a motivation, if you wish. And by using BMO based spaces, we also achieve the endpoint when alpha is not equal to 1. This was unfortunately impossible in the case alpha equals 1 because of, I mean, of course, we could have done this, but there is a log. And at high frequencies, if one wants to embed this in an L2 base Sobolev space, one needs to add an extra small positive parameter. This is where s greater than 2 comes from. And I think I'll stop here. Thank you for your attention.